Gravity. We all think we know what it is, right? It's the thing that pulls an apple to the ground, the thing that keeps the Earth circling the sun. But what if everything we thought we knew was wrong? Today, we're going to dive into how Albert Einstein completely blew up our understanding of gravity, transforming it from some mysterious force into the actual fabric of the universe itself. So let's start with a big question. Is gravity really a force? I mean, think about it. Everything you've learned probably paints it that way. But what if that pull we feel isn't a pull at all? What if it's just the shape of reality, guiding us on our path? Now, before we get to Einstein's massive breakthrough, we have to understand the world he completely turned upside down. For more than 200 years, physics was dominated by one guy, Isaac Newton, and his idea of a perfect clockwork universe. And Newton's rules just make sense. They feel right. He pictured space as this fixed, rigid background, like a giant stage that never changes. And time? Well, time was like a universal clock, ticking away at the exact same pace for everybody, everywhere. In this world, gravity was just a simple, invisible rope pulling things together. It worked, it was elegant, and for a very long time, it seemed absolutely perfect. The official name for this whole setup is classical mechanics, and the core idea is something called inertia. Basically, an object will just keep moving in a straight line forever unless something pushes or pulls on it. So to make a planet curve around the sun, you need a pull. And for Newton, that pull was gravity. But here's the thing. This neat and tidy clockwork universe had a problem. A tiny little crack in its foundation that once people started looking at it closely was going to bring the whole building crashing down. And this is it. This is the problem. The speed of light is always the same. It doesn't matter if you're standing still or blasting through space in a rocket ship. If you measure the speed of a beam of light, you get the exact same number, every single time. Now, this totally breaks Newton's world. If you're on a moving train and you throw a baseball forward, you add the speed of the train to the speed of your throw, right? But light? Nope. Light plays by its own very weird rules. And this is where Einstein's genius just changes the game. He realized that if the speed of light is the one thing that can't change, then something else has to give. And that something else was space and time. He figured they must actually stretch and shrink depending on how you're moving, all to conspire to keep the speed of light constant for everyone. Suddenly, the fixed stage was gone. The universal clock was gone. So what takes their place? A totally new concept, space-time. It's not space and time anymore. It's a single, unified, four-dimensional fabric. Where you are is completely tangled up with when you are. And this isn't just some clever mathematical trick. It's a far more accurate description of the universe we actually live in. It was actually Einstein's old professor, Harman Minkowski, who put it best. He said that space and time on their own are just shadows, and that only their union, space-time, is the true reality. And this brand new fabric would turn out to be the key to unlocking the true secret of gravity. Okay, so if space-time is our new reality, then what in the world is gravity? Well, Einstein realized it's not a force at all, and to help wrap our heads around this, let's use a really simple analogy. I want you to picture a huge rubber sheet, stretched out perfectly flat and tight like a trampoline. If you roll two marbles across it on parallel paths, what happens? Nothing. They just keep rolling in straight lines, staying parallel forever. That's Newton's first law right there. No force, no change in direction. Easy enough. Okay, but what if you saw those two marbles suddenly start to curve towards each other and meet up? In Newton's world, there's only one possible explanation. Some invisible force must be pulling them together. It's gotta be gravity, right? What else could it be? But Einstein comes along and asks a completely different question, a much weirder question. He asks, what if there is no force? What if nothing is pulling on those marbles at all, and yet their paths still end up meeting? How on earth is that possible? And here is the absolutely brilliant answer. Imagine you take a heavy bowling ball and place it right in the middle of our rubber sheet. The sheet isn't flat anymore, is it? It's curved. It's warped. Now if you roll those two marbles again, they are still trying to go in the straightest line possible. But the straightest line on a curved surface is, well, it's a curve. Their paths are now naturally guided toward each other, not by a force, but by the very shape of the surface they're on. There's a technical term for this, straightest possible path on a curved surface. It's called a geodesic. Think about a plane flying from New York to Tokyo. On a flat map, the path looks like a big arc. But that arc is actually the shortest, most direct route on the curved surface of the Earth. It's a geodesic. And what Einstein realized is that objects in space are always just following their geodesics through spacetime. All right, so let's scale this up. Let's take that simple idea of a rubber sheet and a bowling ball and apply it to the entire four-dimensional fabric of our universe. This is the absolute heart of Einstein's general theory of relativity. It's really a beautiful three-step dance. Step 1, mass and energy, like our sun, tells space-time how to curve. The sun creates this huge dip in the fabric of space-time. Step 2, that curve in space-time then tells matter, like the Earth, how to move. The Earth is simply following the straightest possible path it can through that curved space. And step 3, we, standing here on Earth, experience that movement, that path, as the force of gravity. So this slide really puts it all together. On the left, you've got Newton's idea, a mysterious action at a distance force. How does the sun pull on the Earth from 93 million miles away? Newton himself had no idea. On the right, you have Einstein's beautiful answer. The sun doesn't pull on the Earth at all. It just bends the fabric of reality, and the Earth simply follows the curve. Gravity isn't a force, it's geometry. And look, this isn't just a prettier theory or some philosophical word game. Einstein's version of gravity makes incredibly precise predictions that Newton's theory actually gets wrong, and the proof is literally all around us. I mean, check this out. General relativity perfectly explains a tiny, weird wobble in Mercury's orbit that baffled scientists for decades. It predicted that starlight would literally bend as it passes the sun, something that was confirmed back in 1919. It predicted the existence of black holes, places where space-time is so curved that not even light can get out. And get this, the GPS in your phone has to make calculations based on general relativity every single second, or it would be off by miles within a day. And maybe the most amazing prediction of all, ripples in the fabric of space-time itself, gravitational waves, which we finally detected in 2015. So this is the ultimate takeaway, the thing to really let sink in. We aren't just actors moving on a static stage. The stage itself is dynamic. It's bending and warping, shaped by all the matter and energy in it. And its very geometry is what dictates our every move, from a falling apple to the grand orbit of a galaxy. So, no, gravity isn't a force pulling us down. It's the shape of the universe showing us the way. Einstein's revolution taught us that our most basic ideas about reality can be completely overturned. He replaced a mysterious force with the elegant dance of geometry. And it leaves us with this final, thrilling question. If the fabric of reality itself can bend, stretch, and ripple, what other incredible secrets is it still waiting to tell us?